of the course, okay? And if it doesn't make complete sense today, that's okay. But as we work, because I'm going to explain this and we're talking about this over and over and over again throughout the next several weeks. But the process that I'm going to go through today should hopefully kind of lay the groundwork for a lot of the stuff that we're going to do throughout the year, and hopefully make a connection on why the procedures that we go through are kind of validated. Okay, so initially I'm going to do the work all in GeoGebra. Okay, I'll try to write on top of GeoGebra the best I can here to kind of draw my conclusions or create conclusions for you. But I don't know if there's going to be a whole lot that you can actually write down right now. Okay, but it's going to be beneficial to make sure that you watch, maybe ask questions if something doesn't make sense. I just want to demonstrate, yesterday we talked about these ratios, okay? And those are true, but I want to talk about why they're true, okay? Or maybe demonstrate to you that they are true, okay? And then kind of talk about some variations about what happens in regards to my theta, if my theta is bigger than 90 degrees or bigger than 180 degrees or whatever, and how we address these values when that happens. So right now, I want to work in the first quadrant, okay? So I've created this segment, F. That's going to be my initial ray, so I'm not going to move that. But this G, I'm going to let that be my terminating ray. So that one, as we work through the period, that one will move to different quadrants to see the relationships that we're interested in. The idea here, though, is that when I talk about this point, I'm going to rename this point P. And that point P is the x comma y that we were seeing in the definition of a trig function, okay? And how like sine of theta was equal to y over r. Well, the y for this situation right here, whatever the theta is, and I'll bring in theta here in a moment, the y for it would be 3. Does that make sense? Okay, and the r would actually be the length of that red segment. Okay, but we really don't care eventually where P is, whether it's 4, 3, or it's, let's see here, point, whether it's 4, 3, or it's that number right there, okay? Because any point that is on that ray, like P or like C, or any of those C's that any of the infinite C's that can be realized from that ray, okay? When I take that y value divided by the r that is attached to point C, I will always get the same ratio as I get when I take the 3 from point P and divided by the r that is attached to point P. Does that make sense? And the reason for that is because if we look at that right there, that is a right triangle. Would you agree with that? Okay. Is that also a right triangle? Okay. Did both those right triangles have a right angle? Did they both have this angle right here where my cursor is that we're going to call theta here in a moment? Did they both have that? So those two triangles are similar, right? So then if they're similar, then their opposite side divided by their hypotenuse should always be in proportion to one another. So no matter what the numbers are, they should always divide to the same ratio. Does that make sense? Okay. So that's why we really don't care where point P is. Okay. But there are, to understand the principles here, there are questions, there are practices, procedures that do kind of concern ourselves with where point P is as an ordered pair. Eventually, what our interest will be to, let's go -1, less than y, less than 1, and then -1, less than x, less than 1. Our eventual interest will to be make sure that we keep this point P inside this little square right here that has a width of 2 and a height of 2, which would be, obviously, the demarcation lines are 1, -1 on the x and y axis, and that will give us the unit circle. Does that make sense? So eventually we want this thing to be down here and be any P value around here. Because if I can find, again, if I go 4, 3, but then look at the point, let me just write this real quick. X squared plus y squared equals 1. So there's a unit circle. Let me find the intersection of the unit circle with that red line, point C. Okay, so let's hide some stuff here, clean it up a little bit. So what we find out here is if I take the, let's just go real quick. Let's find what would be the length of this red segment right here if this point is 4, 3? Think about, what'd you say? It'd be 5. Why is it 5? Okay, good. So if I'm going to be at 0, 0, then the horizontal distance that I have to travel to get to P, that would be 4 units. Then the vertical distance that I have to travel would be 3 units. So we got that right triangle. So that means the red one has to be 5, right? Okay. So if I want to find, so I don't know what this angle right now is. Okay. I'm going to call it theta. I don't know how big it is. But if I wanted to say the sine of theta right now, based on this triangle, it's from our definition yesterday, it's 3 over r, which would be 3 over 5, which is 0.6, right? Okay. Well, eventually, we don't want to look at the values of 4 and 3. We would much rather look at this point C right here, because it's still on that red ray, correct? But the point C now, okay, is at 0.8, 0.6. And if I use the Pythagorean theorem on that, then this distance right there, that's 0.8. That y distance is 0.6. This would be 1. Does that make sense? What's y divided by r in this case? Sine of theta, because this is still the same theta, right? So y divided by r, but r being 1 is just still y, right? And what's y in this case on this point C? 0.6. Is that the same 0.6 that we saw when we used the 0.43? So any point that I use on there, you know, if I choose that point right there, it's still going to be the sine, it's still going to be 0.6. Okay? Now the division is not going to be as nice, okay, because I'm not dividing by 1. But that's kind of the underlying principle that we're going to go through throughout the course and need to understand to make the course a little bit more comfortable, okay, in regards to, you know, do I really know what I'm doing, or am I just going through procedures, okay, not really understanding why I'm doing that procedure or what results mean to us, okay? So if we, like I said, if we go y divided by r, in this case, it would be 3 divided by 5. Obviously, we get our 0.6. Now, if I look at this angle, so let GeoGebra calculate this angle real quick for us. Just 36.8699. Okay, and I think we can probably justify that that's not the exact value. Okay, but it'd be close enough. We'll go to 4 decimal places. I'm going to call that theta. Remember, there we go. Okay, so that's the theta that we're interested in. Let's make it a little bit bigger. All right, so 36.8699, okay? If we were to type in, so we know that y divided by r gave us 0.6, right? Well, if I type in sine of 36.8699, okay, or just a sine of theta, does it give me the same 0.6? Okay. So that right there is hopefully drawing the link to show us that the sine of theta is indeed the same thing as the opposite side of this triangle, which is the y value, divided by the hypotenuse of this triangle, which is the r value. Does that kind of make sense? Okay. So let's go through, and I typed in that right there. So the calculator is doing us a service here of rounding pretty well. But if I just typed in the theta, when I do it that way, what it's going to do is it's going to recall, it's going to pull off this entire value, and you see that it is 0.6 as well. Okay. But if I change it, so if I go here, okay, so if I go, so this is still a 3-4 triangle, 3-4-5 triangle, right? Okay. Now, if I go sine of 53.130, it'd be y divided by r. So 4 divided by 5. 4 divided by 5 is 0.8, right? Are we seeing right here, sine of theta is still 0.8? Okay, now here, because of the way I typed it in, it was, so let's do this. Let's go. So let's say the C number here is the x of point P divided by the square root of the x of point P squared plus the y of point P squared, and this should actually be, I wanted the y of point P, right? So I put this formula in, so that's basically taking y divided by, and this thing here is a formula for finding r, correct? Okay. So if I do that, I don't know if I close my parentheses off. No. 0.8. Does that make sense, everybody? So this right there is coming up with the formulas that were defined in the blue box yesterday as y over r, okay, for sine. This is being evaluated as the sine of that. So your calculator probably right now is programmed with a, I have to remember which way, it's either a Maclaurin or a Taylor series from calculus. And I'll show it to you at some point. It uses a bunch of sums of like factorials, okay, which will estimate then our sine curve. So our calculator is probably programmed to evaluate sines of thetas using some other tool than y divided by r. Does that make sense? Okay, so this number here is not being calculated by GeoGebra the same way that that number is being calculated. Okay, but we're seeing that they're the same, right? If I go sine, let's put this point out here at 7, 5. Okay, you see that the sine is evaluating it as 0.5812, and the formula of 5 divided by r is still giving me that 0.5812. Does that kind of make sense to everybody? Okay. Any point, let's see here. Any point that we put in the coordinate plane is going to be calculated the same way. Now, if I look over here, let's go -3, 4, we still get the same results, right? Okay. So now we're asking, what is the sine of 100 and, I'm going to say 127 degrees. Sine of 127 degrees. It's saying it's 0.8. Okay? Because we can go, again, the y value would be 4, and the r value would be 5. Now, the question is, well, I thought sine, cosine, and tangent were just for right triangles. Okay? This is not an angle of a right triangle, correct? So what happens is that we can actually take this triangle right here. Okay? Which that triangle, this value here would be 4. Now this value would be -3, right? And that would be 5. Okay? We could take that triangle. Okay? Take the y-axis. Reflect it. Okay, so let's reflect that over here. So it would be, I'll do it in blue here. We'll be looking at that triangle. This would be 3. That would be 4. This would be 5. Does that make sense? Okay. If I look at y divided by r for this triangle here, is that the same as the y divided by r for this blue triangle over here? Okay. So what that tells me then is that when I want to know something about a 126 degree, 0.8699 degree angle, okay, this triangle right here, or this angle right there, that blue angle, is going to tell me everything I need to know about it. So let's go ahead and see that kind of in play here. If I take, so what would, if I put this green angle out to here, that'd be 180 degrees, right? Okay, so how can I find this angle right here? Okay, so that's going to be the supplement of 126, right, or 127. So I'm going to say 180 degrees minus theta, and it gives me 53.13 degrees, right? Okay, so I'm going to, let's see if we can do this in another window, make it a little bit easier to visualize. All right, so that red angle is 53.13 degrees, which is exactly the same thing as this angle down here where my cursor is. Does that make sense? Okay. And if I can find the sine of this angle, so doing that, this point, going back over to this right here, if that's 3, that's 4, that's 5, the sine of 53.1301 is going to be the same thing now as the sine of 126.8699 because it's ultimately using the same y and r values. Does that make sense? Okay, so just to justify that, if we were to take one of our calculators and type in what is the sine of, now the red angle, they're calling it beta. So sine of beta, and it gives me 0.8, right? Okay, we already have right here the sine of theta, and we see it, they're the same. Now, if I ask you to look at those two values, as I move this thing around, okay, as I move that point, are those two values always the same? Okay, so people always ask, and it's never illustrated or explained in textbooks, okay, but why can we use this right triangle, okay, and essentially talking about then this angle right here to tell me something about this angle, and it's because of that reflection that we can do. Does that make sense? And we're using the same y values, all right? Now the question says, well, can I do the same thing if I'm going down here at this point. Okay, so now I'm looking at 216.8699, right? Well, now the triangle that I'm interested in, and we're probably going to run out of time here in a moment, but and we'll pick up with this on Monday, but this is the right triangle that I'm interested in now. So would it make sense that that angle right there is ballpark 36.8699 degrees? Because this is 180 right across here, right? And I'm going 216, so that's 36.8699. Well, if I come back into using, so how does this angle right here relate to that angle right there from geometry? Starts with a V. Vertical angles. Vertical angles are what's going on? They're equal, they're congruent. So if I can know something about that angle in the first quadrant, which I do, I know the sine of that 36.18 or 0.8699 number. I know that's I think we said it was 0.8, right? We know that sine, 0.8. Well then for this angle, the y divided by r better be sorry, it was in this case it was 3 divided by 5, sorry. So 3 divided by 5 is 0.6, okay? So it should give 0.6. So then in this triangle here, it should be the same y divided by r. That's 5. But now this y is what kind of number? In what quadrant are we in? Third quadrant. So the y is negative. So we've got negative 3 divided by 5. And that's negative 0.6. So that's why that's negative 0.6 right there. Does that make sense? Okay. So we're going to, when I ask, the sine of 210, why is the sine of 210 different than the sine of 30? They're both 0.5. But sine of 210 is negative 0.5 because the y value in the third quadrant, because that's where 210 terminates, right? That y value is a negative because it's in the third quadrant. So we go y divided by r is a negative divided by a positive. Okay? So we'll stop there. On Monday, I'll give you a graphic here. It's pretty easy to remember that will tell you, okay, if I've got an angle between 0 and 90, these are the trig ratios that are positive. And then automatically, by default, we'll know which ones are negative. If I'm between 90 and 180, 180 and 270, and 270 and 360. Okay? But I want to make sure, and we might even talk about the whole period again on Monday, that we understand why we can use that, sometimes we refer to it as like a reference angle. Why we talked about that smaller angle to tell me about a bigger angle.
Pardon interruption. Here in the next minute or so, we will be conducting a practice fire drill for today. Again, this will be a practice fire